All right. This is all most easily explained in terms of an example, and it's always pleasant to see the example apply to something practical. So what I've done here is dug up a data sheet. This is a commonly used transistor now. This has appeared in a bunch of designs. I've used it in various designs. I've worked with people who've incorporated it into their designs. So this is a very common and typical RF transistor. It's a NPN type transistor, but we don't really need to know that to do the work we're going to do here. It's a silicon bipolar transistor. Again, you should recognize what those terms mean, but none of that really matters for what we're about to do, because all we're going to need to know are the S parameters of this transistor. Again, I'm just trying to show you that this is a real device here. So in the datasheet for this transistor, it lists S parameters. The S parameters are always listed for a particular set of conditions. It's in the common emitter configuration. The reference impedance is 50 ohms. The collector emitter bias voltage is 2.7 volts, and the collector current is 5 milliamps. These are all very typical values. In later lectures, when we design amplifiers, you will have the chance to grapple with all of these concepts. All that we need to know here are the S parameters for the frequency that we're interested in. Let's work at 1 gigahertz. So 1 gigahertz in this table is right here. It's this line right here. And we see that the table gives us the magnitude and the phase of S11. We see the magnitude and phase of S21 and so on for the 4S parameters. Now, one reason why I want to do this example is to give you also practice in interpreting data sheets. So datasheet authors are frequently somewhat sloppy. For example, here, these values are all in degrees, although it's not really indicated that these are phases in degrees. It's just kind of a convention among RF engineers that that's going to be the case. So, for example, S11 here is 0.48 at an angle of minus 149 degrees, or it has this value in terms of real and imaginary components. Okay? Is this transistor stable at 1 gigahertz? If the source impedance is Z0, right? If the source impedance is equal to the reference impedance, then we get gamma S equals 0. And the load impedance is such that gamma sub L is 0.25 plus J 0.25. So are we stable when we terminate this transistor in this particular set of impedances? Well, here is the embedded input reflection coefficient, its magnitude. I will leave it to you to work through the calculation and see that this is true. And please do this, because this is a skill you will need countless times in the rest of the semester. So make sure you confirm you get the same numbers as I do. I get 0.622. 0.622 is less than 1. So far, so good. I need to check the output embedded reflection coefficient. Here's the expression. The value I get is 0.490. That's less than 1, so again, we're good. Gamma sub S is 0. That's less than 1, so that's good. Gamma sub L, the magnitude is 0.354. That's less than 1, so that's also good. So we've satisfied all 4 inequalities that are required to establish stability here. Therefore, this transistor is stable at 1 gigahertz when the source and load impedance are as indicated here. Now, what happens if we change the output impedance? So the problem here is exactly the same as on the previous slide, except now I have changed the load impedance such that its new reflection coefficient is 0.5 plus J 0.75. Well, in this case, the embedded input reflection coefficient has changed. It's 1.052. Is that less than 1? No, it's not less than 1. So the change in the output reflection coefficient, the change in the output impedance, has resulted in a violation of this inequality. So we don't really need to go any further. We already know now it's not stable under these conditions. But just for the sake of completeness, let's go ahead and do the other 3. Here's the embedded output reflection coefficient magnitude. It has not changed. It has not changed because the S parameters of the 2-port haven't changed. and the source impedance hasn't changed. So this is the same as it was in the previous problem. The source impedance is still equal to the reference impedance, so that hasn't changed. And the load impedance has changed, so we get a new magnitude here. That's less than 1. So if this had been less than 1, we would have been okay. The only thing that's keeping us from stability here is failing this inequality. Bottom line is here, we are not stable under these conditions. Okay, the second method is brute force testing. So I'm going to use the same example, the same transistor with the same S parameters and the same frequency, 1 gigahertz, and do brute force testing. So what I've done here is I've made this map of the magnitude of the output reflection coefficient, output embedded reflection coefficient. So here's the real part of gamma sub S. Here's the imaginary part of gamma sub S, and the color indicates the magnitude of the reflection coefficient. All right. Now this is a heat map style color scheme, and in this color scheme, any color more yellow or trending towards white above this line is greater than 1. So we see that there's a region over here for which we will not be able to achieve stability. So this region over here will correspond to values of the source impedance for which we cannot achieve stability. We can do the same thing for the input reflection coefficient, the input embedded reflection coefficient. So here's the real part of gamma sub L, here's the imaginary part of gamma sub L, and then the color indicates the magnitude of the embedded input reflection coefficient. And once again, we see there's a range of values over here for which we cannot satisfy the inequalities. So we see that at 1 gigahertz, this transistor is conditionally stable. There are some values of source and load impedance for which we achieve stability. There are others for which we don't. So we refer to this as being conditionally stable, a conditionally stable transistor at 1 gigahertz. Now, I want to make a connection back to an idea that you may have seen in a previous course, probably electromagnetics, and that is the concept of the Smith chart. So first, if you had a bad time with Smith charts in a previous course, don't worry about it. We don't necessarily use them here. You're free to use them here. In fact, many times when this course is taught by other instructors, they emphasize the use of the Smith chart. I'm kind of neutral on the whole idea. If you enjoy Smith charts, you will find them to be useful. And in fact, they pay dividends in some particular problems. But in general, you won't need this idea. I simply want to point out where the connection is. And that's this. These maps I'm making of reflection coefficient are in fact Smith charts. The Smith chart boundary circle is gamma equals 1. So that circle and that circle are the same thing. And in fact, if I superimpose the Smith chart here, there's one axis. There's arcs that go like this. Right? And then there's circles that go like this. So that's how the Smith chart would appear if I were to draw it on this map. And once you know that, you can use all the techniques associated with Smith charts to manipulate these values. So this is why Smith charts are popular among RF engineers. Once you understand how a Smith chart works and how changes in the circuitry can be reflected as geometrical manipulations of this chart, you can, for example, manipulate the stability of devices. So there's a connection.